Let's get ready to do exam 2A. Grab your calculators, your pencils, and some paper, and please keep all hands and feet inside of the desk space throughout the course of this practice exam ride. So as you guys know, I'm Virginia. My email is down there if you guys have any questions or want to get in contact. And don't forget to work through these problems on your own too. And make sure you can recreate the calculations on your Chem 112 approved calculator. Okay, let's get into it. So the first question asks us to identify the role of each species in the following reaction using Bronsted-Lowry definitions of acids and bases. So Bronsted-Lowry is pretty trad. This definition is just the idea that acids are going to donate H plus, or protons, and bases are going to do the opposite. They're going to accept the H plus. Okay, so let's just see how our molecules change and see which is donating a proton and which is accepting a proton. Okay, so what I see here is this hydrogen ends up leaving this carboxylic acid organic molecule. And I see that the water is going from having 2 hydrogens to having 3 hydrogens and a positive charge now. So since this first molecule is losing the hydrogen, this is going to be the acid, making water the base. Okay, so then we need to think, is this a strong or a weak acid? So it's not one of our 7 strongs, so it's definitely weak. The carboxylic acids are weak acids. Okay. So hopefully you guys can see how this molecule and this molecule are related, right? They're pretty much the same thing, just plus or minus a hydrogen. And so we would call these a conjugate pair. And so we know that the conjugate of a weak acid, which is what we start with a weak acid. On the right we have its conjugate. And the conjugate of a weak acid is going to be a weak base. Okay, and then hopefully you guys can see that this water and the hydronium are related to each other. Now, is water a strong base? No, it's not a strong base. It's a weak base here. And so the conjugate of a weak base is going to be a weak acid. Okay, so now we just have to find the right answer choice. And it looks like it is C. Okay, so you just got to track those protons. Okay, number 2 is referring to one of my personal favorite demos, where you mix the 2 salts together and under the beaker you put a little bit of water and a wood block. And then after you mix the salts, you've frozen that water. So they want us to figure out something about like the thermodynamics of that demo. And so when you have the beaker freezing to the block, well, we know if water's freezing, it must be getting colder. And so what that tells me is that the reaction is sucking heat in from the surroundings, which is that water. So when we sense something getting colder, That means it's endothermic. The heat is entering the reaction, and that's why we feel cold. And endothermic, we know, has a positive delta H. Okay. So now, for the delta S portion, we need to look at the phases, because different phases are going to have different entropy levels. Okay, so I've written down here below kind of how we think about phases in terms of entropy. So solids are very rigid. There's not a large number of conformations they can take, so they have a low entropy. Whereas gases are wild. They can bounce around and spin and flip and do all kinds of crazy things. So we can look at the phases on the reaction to see what happens in terms of entropy. So we start on the left with a total of 3 moles of solids. So we just have a bunch of solids. And then on the right, we have something, 1 mole of something aqueous, 2 moles of gas, and 10 moles of liquid. And so all of the phases that our reactants are making are higher entropy phase, or I'm sorry, that our reactants turn into, so that our products are. Our products are all higher entropy phases. And also we just have a lot more moles of different things, which also increases the entropy, because you can have a bunch of different neighbors then. Okay, and so when we have increased entropy, that's positive. Okay, so we've sort of eliminated 3 of the options by figuring out those signs, but now we need to figure out when it's spontaneous. And so we know that for spontaneous, we need delta G to be negative. So we'll have something that we want to be negative equal to something that's positive minus temperature times something that's also positive. Okay, so how I see this is we have a positive minus another positive. We want this to be negative, so we need to make this portion big, so that we have something bigger to subtract off to make it negative. And so for us to do that, we want to work at higher temperatures. Okay, so for this to be spontaneous, we want to be at high temperatures E. Another way to think about this too is generally exothermic reactions are more favorable. So this endothermic reaction, not so great. The positive delta S though is good. That is favorable. And so we want to maximize the favorable thing. And so we can maximize this by heating it up. Okay, so that's just another way to think about it. Okay, for number 3, we're making ammonia. We have the Haber process. Woo! Okay, and so we have this graph, and they want us to figure out what KEQ is for the reaction. So I've gone ahead and written incorrectly, there we go, the KEQ expression for this reaction. And so for KEQ, we want to put in equilibrium concentrations into these values. And so what we want to look for equilibrium is when the concentrations are steady. We can't see any change. Okay, and so that's going to be where the lines level out. And so we can come back over to this plot and see that the H2 line levels off at 1.5, and the units on the y-axis are moles per liter, which is the same as molarity, so it's good news. the ammonia line levels off at 1 molar, and the N2 levels off at 0.5 molar. And so now we just have to take those concentrations and plug them into our KEQ expression. Okay, so for the ammonia, we'll have the 1 molar from the plot squared. For N2, we'll have 0.5 molar. For H2, we'll have 1.5 molar cubed. Okay, and so when you go ahead and evaluate that, you get 0.59. Okay, so let's see, is this products or reactants favored? And so we know that when KEQ is less than 1, that's going to be reactants favored, because reactants are our denominator. Okay, so make sure you're comfortable writing these KEQ expressions and then plugging into them to get the KEQ values. Okay, we have this crazy metal complex. Okay, and they want us to figure out how many moles of ions we'll end up making when we dissolve this. Okay, so let's write what happens when we put it in water. So everything that's inside of the brackets is stuck together. It's going to stay the same. So we'll have the chromium, and then we'll have the ligands that are complex to the chromium. So we have the ammonia, 4 of those, and 2 chlorines. So those are staying together. But what's happening now is the Cl is dissociating. And we know that chloride is a -1 charge. So this will be aqueous. And so if we're losing a -1 charge, our whole complex then must be +1. Okay, so we're going to keep everything inside the brackets together, and then we'll have just whatever is outside of the brackets dissociating away. Okay, so if we just have 1 mole of reactant, we'll make 2 moles of products. Okay, so we'll have just 2 moles of ions. If you wanted to figure out what the charge on the chromium is, then we'd have to pull off the ligands. And so we know that ammonia is neutral. And like we said before, chlorine has a -1, and we have 2 of these. So everything that's complex to the metal is going to have an overall -2 charge. And so if they'd asked, we could tell them then that the chromium must be just +1 charge. I'm sorry. The chromium must be +3 charge, because the overall complex has a positive charge, and we're putting something that's -2 on it, so the chromium would be +3. But it's not asking for that. I just wanted to give you guys a heads up. Okay, number 5, we have another entropy question. And it's asking us which of the following species will have the greatest absolute entropy at 0 degrees. And so I wrote the things that I consider in order in terms of entropy. So first, I look at temperature. They tell us that all of these are at the same temperature, so I'm not going to worry about that. Then I look at the phases, because we know solids are the least entropic, whereas gases are the most entropic phase. So I can go ahead and eliminate anything that's not a gas, because it's asking us for things with the most entropy. So next, I'm going to look at the number of bonded atoms. So the more bonded atoms you have, the more kind of crazy conformations the molecules can take, and so the more entropy they would be. And so neon doesn't have any bonded atoms, so I'm going to eliminate that. And BH3 has fewer bonded atoms than the methane or the CH2F2. Okay, so now let's look at the fourth consideration, which is size. So we know that CH2F2 is going to be much heavier, just because fluorine is bigger than a hydrogen. And so its electron clouds can do weirder deformations and such. And so that will have the highest entropy. Okay, number 6, they give us pictures of different molecules, and they tell us the reaction that these molecules are abiding by. They then want us to predict which way the reaction will proceed to get toward equilibrium. And so I've written here the expression for Q, and it's very similar to our KEQ expressions. It's just we can put any kinds of concentrations into it, and then we'll compare that to K. So if we do that and we find that our Q is less than KEQ, that would mean we have too many reactants. We need to make more products. So we're going to shift to the right, toward products. If our Q is greater than KEQ, that means we have too many products. Remember, it's products over reactants. And so this would need to shift to the left. And if Q is equal to KEQ, then it's already at equilibrium, and there will be no shift. Okay, so whenever I have a problem with pictures of molecules, I go through and just count and convert the molecules to some concentration. So I've gone ahead and done that for each picture. And so now what we'll do is just take it one system at a time. We'll have system 1. So we'll have our Q that we're trying to find. So we have AB squared on top. And we can see from the diagram that we have 6 molar AB, that's squared, divided by our concentration of A, which is just 1, times our concentration of B, which is also just 1. So the Q here is going to be 36. Don't even need a calculator. And so the 36, which is our Q, is greater than the 1.5 KEQ. So we have too many products around, and the reaction is going to shift to the left. Okay, so I'm just going to put a little arrow there so we remember what we decided for system 1. And we're going to use the same process for systems 2 and 3. Okay, so for system 2, now we have for our AB 3 molar just squared divided by our concentration of A, which is also 3 molar, times our concentration of B, which is 2 molar, and we get a Q value of 9.6, which is equal to 1.5. Okay, so in this case our Q of 1.5 is equal to the KEQ of 1.5. So this system is at equilibrium, and so there will be no shift. Just put a little circle there. Okay, last one, we'll do the same thing for system 3. We'll have our AB concentration, which is 2. That'll be squared, divided by our concentration of the A2, which is going to be 3, times the concentration of the B2, which is also 3, and this is equal to 4/9, which is the same as 0.44444. Fractions with 9 are my favorite. Okay. So our 0.444 is less than the K of 1.5. So that means we have too many reactants, and the reaction will shift to the right. Okay, and it looks like A is the option that matches what we decided. Okay, for number 7, we're trying to figure out which reaction has a decrease in entropy. And so when we look at these questions, we're going to use the phases in the reactions, because we know different phases have different entropy levels. So I've written the ranking down here below, where solids have much lower entropy than, say, gases. Okay, so if we look at A, we have solid and gas, and we go to form many more moles of gas. So I would say this is an increase in entropy. For B, we have a solid, dissolve it in water, and now we have aqueous solutions. And aqueous is a higher entropy phase, so that's also going to be an increase in entropy. For C, we have evaporation, and that's going from liquid to gas, so it's going to a higher entropy phase. This is positive. Okay, for D, we have 2 aqueous things on the left, and we go to form 1 aqueous thing. And so this is a little bit subtle, but this is going to be the decrease in entropy. And the reason that this is the case is, like, if we have a box and it has some green stuff in it, but it also has some pink stuff in it, the molecules see different things than if it's just something, a box with orange molecules in it. Right? The one with only the orange molecules is more uniform. And so this box with 2 different molecules has a higher entropy. So when we're going from higher entropy down to lower entropy. But let's check E just to make sure. So we're going from liquid and gas to lots of gas. We're going from 13 moles of gas over here to 18 moles of gas, and the liquid is also being able to expand. So that would be an increase also. So the answer here, while subtle, is in fact D. Okay, back to the Haber process. So they want us to figure out at what temperature this reaction becomes non-spontaneous. And they give us information about delta G, delta H, delta S, etc. And so we know that the cutoff between spontaneous and non-spontaneous is going to be when delta G equals 0, because we know it's positive for non-spontaneous, it's negative for spontaneous reactions, and so the cutoff right between there is 0. So what we want to do is say 0 equals delta H minus T delta S, and then try to figure out what this temperature is that makes this true. So what we actually need is just information about delta H and delta S, not about delta G in this table. So we're actually not going to use this information at all, because this is only true at 298 Kelvin, because it's the standard delta G. Okay, so what they give us are delta H's of formation for each of these individual molecules. So what we're going to have to do is get an overall delta H of reaction by doing products minus reactants. So the delta H formation for the products minus the delta H of formation for the reactants. Okay, so we're going to need to use the reaction, so we have the coefficients straight, and then we're just going to have to make sure we match up the right delta H's to the right molecules. Okay, so it's delta H of reaction for the products is going to be 2 times the value for NH3. So it's products minus, and then just 1 times the value for N2 plus 3 times the value for H2. Okay. Excuse me. So when we put this in, we're going to have 2 times, and we need the gaseous ammonia, not the aqueous ammonia. Okay, we have to match the phases. So this will be negative 46.11 kilojoules per mole. Minus delta H formation for N2 gas is 0, because it's in its standard state. And the delta H of formation for H2 is also going to be 0, because it's also in its standard state. So the delta H for this reaction overall is going to be negative 92.22 kilojoules. So let's go ahead and write that over here so we can keep track. Okay, so now we can use similar idea to figure out what our delta S is. We'll still do products minus reactants. Okay, so same setup, just different numbers from the table now. So we'll still have 2 times the value for ammonia gas. And it's kind of cool there. We can see that the gaseous ammonia does have a higher entropy than the aqueous ammonia. This is in joules per mole Kelvin. Now minus 1 times the value for N2, which is 191.5 joules per mole Kelvin. And then we'll have 3 times, the value for H2, which is 130.59 joules per mole Kelvin. Oh, you guys probably can't see that at all because of the silly finger that's pointing. Let me rewrite that. Okay, hopefully that's better. And when you go ahead and evaluate, you find out that this change in entropy for the whole reaction is equal to negative 198.59 units are joules per Kelvin. Okay, so I'll mark that here. Okay, so now it's time to combine these two and solve for our temperature. Okay, so we know we want to set delta G equal to 0. And then we can put in our enthalpy. So we need that minus T, and then we need our delta S. But hopefully you guys have realized that the units on delta H and delta S are different. We have 1 in kilojoules and 1 in joules. And so we need to, sorry, this should really be just per Kelvin because we multiplied by the moles when we did our calculations. So we got to put our delta S in terms of kilojoules. So I'm going to write 0.19859. And now this is just kilojoules per Kelvin. Okay, that delta S will sneak up on you, so make sure you're paying attention to the units on those. Okay, so if we do some rearranging, we'll have 92.22 is going to be equal to 0.19859 T. When we divide over to solve for T, we get that it is equal to 464 Kelvin. And we know it's Kelvin because of the units on delta S. So we go to look at our answers. Shoot, they're in Celsius. But we can handle that, right? We're just going to subtract off the 273. And we'll get the answer to be 191 degrees Celsius. Okay, so lots of products minus reactants. You have to remember that the cutoff for spontaneity is when delta G is equal to 0. And then you plug your values in with matching units to solve for temperature. You get C. Okay. Here we have a problem where they give us a reaction and it's KEQ. And they give us some initial conditions. And so we have initial conditions. They're asking us for equilibrium. And so we're going to have to ice it out. Okay, so I've already started to set up the ice table here. We have none of the N2 or O2 in the beginning, but we have 0.6 moles of the NO in a 1 liter vessel, so that's just 0.6 molar. Why not use molar in your tables? Okay, and so hopefully you guys can see that this reaction is going to proceed to the left, because right now we don't have any reactants to begin. So there's only one way for this reaction to go. Okay, so what's going to end up happening is our change is going to be negative from the product side. And so our equilibrium value for the NO will be 0.6 minus 2x. The change for the N2 will just be plus 1x. Change for the O2 plus 1x. Equilibrium values will be equal to x. Okay, so now we're going to take this equilibrium row and put the values into the KEQ expression that I've set up. So we have products to their coefficients divided by reactants to their coefficients. If you're not sure where to start with one of these problems, it is never a bad idea to write your KEQ expression, okay? So maybe get into the habit of starting by writing those expressions. Okay, so once we plug everything in and set it equal to our KEQ value, maybe you can see that we could rewrite this denominator as x squared, because it was something multiplied by itself. And we have a square on the top also. So what we can do to make the math simpler is to go ahead and take the square root of both sides. Okay, I'm going to erase the ice table now so we have room for the algebra. Okay, so when we take the square root of both sides, what we'll have is 0.02025 equal to 0.6 minus 2x divided by x. So we can multiply over to get 0.02025x being equal to 0.6 minus 2x. Okay. And then I'm going to move the 2x over, add it over, so we'll have 2.02025x is equal to 0.6. And then we'll divide both sides by the 2.02 number to get that x is equal to 0.297. Okay, but before we do anything, we got to remember what the x was. So I erased the ice table, but let's remember that they're asking us for the concentration of N2. And if you look back at the ice table that you've written down, you can see that the equilibrium line for the N2 value was just going to be equal to x. Okay, so the concentration at equilibrium of N2 is equal to the 0.279, or 2.97 molar. But it's always good to take your x, not just circle it right away, and make sure that you're plugging it back into your ice table to get the appropriate numbers. So here we have a plot, and it's telling us something about energy. It gives us a line for temperature. Our temperature is our x-axis. We have a line for our T delta S and a line for delta H. So I like to start with delta H, because usually it's easiest. And so because this line is coming in at a negative number, that just tells us that we have a negative delta H. We have an exothermic process. Okay, and so for the delta S sign, we can look and see as we increase temperature, this line decreases. So that means we must have a negative delta S. Okay. So we can eliminate the first statement as an option. And so for the second statement, it wants us to decide if the reaction is at equilibrium at 400 Kelvin. So we don't have exact values for delta H or delta S, but we can see that they're equal, or that delta H and T delta S are equal at that temperature. So what we'd have is some negative delta H, and we'd be subtracting off an equal sized negative delta S. So we can say, like, let's pretend delta H is -5. And we know T delta S is the same, so it's also going to be -5. This would be equal to 0, right? You'd have something minus itself. And we know that when delta G equals 0, we are indeed at equilibrium. Okay, so statement 2 seems to be true. For statement 3, they say the reaction is spontaneous at 350 Kelvin. Okay, oops. So we know 350 Kelvin is going to be lower than 400 Kelvin. Okay, so do you guys see how the T delta S value there is less negative than the delta H value? So if we stick with our time when we pretend that delta H is -5, let's say that delta S is maybe something like -4. You know, it's just less negative. Let's see how this would play out. We'd have -5 minus -4. So this would be equal to -1. And so we know when delta G is negative, that's spontaneous. Okay, so 2 and 3 seem to be true. And another way you could think about the third statement is when you have a negative delta S that's unfavorable, we want to make it colder and colder to minimize that unfavorable contribution. And so this would be spontaneous at cooler temperatures. And we know that 400 is at cutoff, so any temperature below 400 Kelvin will be spontaneous. So for question 11, they want us to figure out the KEQ value for reaction C, given the KEQs for A and B. So A and B are different reactions than C, but it's such that we can add them together to make reaction C. The only issue is we can't do it quite yet. Not everything cancels how we would want it to. So when I figure out what we would have to do to the reactions, I like to look at the reaction that we care about, which is C, and then look at A and B and see what's in those that we don't need to be in C. Okay, so I see that we have protons in the first two reactions that aren't present in our third reaction. So I need to cancel those. So we'll have to flip one of the reactions over so we can have them cancel from products to reactant sides. So I'm going to flip the second reaction because that gets the acetate on the reactant side like we need and the acetic acid on the product side like we need. Okay, so let me just, let's just cross that one out. and instead we'll have CH3COO minus plus H plus makes the acetic acid. And so when we flip a reaction over, what we actually are going to do to the KEQ is do 1 over KEQ. So the original value was this 1.8 times 10 to the minus 5. Okay, and so we're changing what's a product and what's a reactant. So we're just going to flip the K expression over, which is the same as doing 1 divided by that KEQ. Okay, and so now we will have canceled the H pluses. And when we combine them, we'll have the acetate where we need it. We'll have the water where we need it. We'll have the acetic acid where we need it. And we'll have the hydroxide where we need it. Okay, so we're going to combine this top reaction with the rewritten reaction to make our new equation. And so when we combine our KEQs, we're going to multiply them together. So KEQ for reaction C is going to be equal to KEQ for A, which we didn't change at all. We're going to multiply that together with 1 over KEQ for B, because we did go ahead and flip that. We didn't have to change any of the multipliers, any of the coefficients, but if we did, then we would just have to put our multiplier in the power. So if we had doubled the coefficients, we would square the KEQ. If we'd halved them, then we would take the square root of the KEQ, so on and so forth. And so we can put the actual values in. So we'll have 1 times 10 to the negative 14th times 1 over 1.8 times 10 to the negative 5. And the answer you end up getting is, and this ends up being 5.55555, let's call it 6, times 10 to the negative 10. So that's super reactants favored. And it is also answer choice A.